Okay, we want to talk a little bit about a concept that the ACI and concrete designers use quite frequently, and it's a concept that's referred to as reinforcement ratio. So far in the problems that you're given, we always say, hey, you got this many bars, you got 3 number 8s, you got 4 number 9s, and we give you that, and we've done an evaluation problem or two, but what that really doesn't answer is a question that I could ask you, which would go like this. If I had 42 number 11s in a beam, would that be a lot of steel? If I had 42 number 11s in a beam, would that be a lot of steel? The answer is, I don't know. Tell me how big the beam is. So the raw value of area steel, 42.77 square inches, 99.12 square inches. That is not really the full story, because you got to know how big the beam is that this area of steel goes into. So I could have 4 number 9 bars, and that could be, for a very small beam, that could be a lot of steel. I could have 44 number 11s in a beam, and because the beam's very large, that might not be a lot of steel. So it just doesn't depend on area of steel alone, even though, in our evaluation problems, area steel seems to be driving a lot of stuff. Okay, it's the very first calculation we do. T is equal to AS Fy. But there are limits to that. But instead of talking, when we get into design, about just area steel, even though that's what we want to ultimately come up with, possibly in design, we talk about a concept called reinforcement ratio, which the reinforcement ratio is given a Greek symbol, looks like a P, called a rho, okay? And the reinforcement ratio is simply the area of steel divided by B times D. And the concept here is, pretty straightforward. If I have a range of steel that I could use in a beam, why don't we, because raw amounts of area steel won't do that. I can't say, hey, in a beam you can only use up to 44 square inches of steel. I can't do that, can I? Because the beam might be really, really big. At the same time, I can't say, hey, for the smallest amount of steel you can use is 3 square inches. Because I can't say that, because I might have a really small beam. So the concept of reinforcement ratios is a concept that people get very familiar with. So it's simply the area of steel divided by B times D.
You do it all the same if you got cables instead of, if you got cables in with it?
If you have cables, the steel cables, like they still have an area. So, but anyway, this concept of reinforcement ratio is something that's going to get a lot of play as you come down. Now that formula can be rearranged. If you want to, if you had a reinforcement ratio, and we'll do this in design coming up here, but you'll see it expressed this way. Where area steel is rho times B times D. So, this general concept of reinforcement ratio is going to be applied as we go forward and talk about design, but I want you to see that. The concept really is how much steel can you use. There has to be a maximum amount of steel, right, in a beam. If there wasn't a maximum, what could ultimately happen in our beam? A what? Well, yeah, no concrete, but let's say there was a lot of steel on the bottom, a whole bunch. And I could have such a big tension force, what would happen to my beam? It would crush in compression. That's not good, because if we like our beams, if they were going to fail, we would like them to fail how? Slowly, in a ductile type fashion. Slow type failure in concrete would be a failure that's initiated on which side of the beam? The tension side. Because as the steel would begin to yield, what would I visually observe in my beam? Cracking. Okay? So we don't want so much steel that the beam fails in compression. That'd be bad. They call that an over-reinforced beam. Nowadays they call it a compression-controlled beam. Bad. Wouldn't want that. On the downside of it, small amounts of steel, there has to be a limiting amount on the small end. Because what would happen if I had a really big beam and I just had one number 3 in? I mean, I had a beam that was 8 feet wide and 16 feet deep, and I had one number 3 in. I mean, besides the fact that, but it'd fail and, before you pulled the forms out just about, what would happen theoretically? Well, the concrete would have such a big tensile capacity that it would carry tension loads for a time being until the concrete cracked. And as soon as the concrete cracked, where does all the tension have to go to? To the steel. Now you got this big tensile area of the concrete, all of a sudden it cracks, and everything tries to go to that one number 3. What happens? Number 3 snaps. See you later. Okay? So that'd be bad. So it'd be bad to have it fail in compression. It'd be bad to have it fail like if there wasn't enough steel. We'd like things to fail ductily. And again, what the ACI code's going to give us is it's going to give us direction of what the range of reinforcement ratio is that my beams will behave in a ductile fashion. Okay? So as we go to the design, that's sort of one of the controlling features of design, is they're going to say, hey, you got this much, this range of reinforcement ratio that you can, sort of design within. Don't go over it, don't go under it. If you go over it one way, your beam's going to be a compression controlled beam, and that's not good. We want our beams to be tension controlled. Tension controlled beam for concrete, and they do this based on strain in the steel, but the strain in the tension steel that is greater, you'll see this one, we'll talk about this in a little while, greater than 0.005 inches per inch. That ensures that you have a tension controlled situation, which is what we like, So, all righty?